Good morning, everyone. So I appreciate that you arrived so early. And we are going to discuss polarized matter. So these are very wide range of matter. For example, if you want to think about a specific one, is water. And we think about a system that has many dipoles inside. And these systems are arranged somehow in space. And this is a finite system, and then we are asking questions like how do we calculate the electric field due to this polarized matter. So we are giving the polarization field, and we want to know the electric field. That's one type of problem. And later on in the second part of the course, we'll do the opposite. Given that we know something about the electric field, what is the polarization field? So these are two types of questions. It's like a hen and the egg kind of thing. What comes first? So it depends on the problem that you know. Sometimes you have information on the polarization of the matter. Someone took dipoles and stuck them inside in some organization, and let's say you know it, then you calculate the electric field. Sometimes you don't know exactly what is the polarization. You have some information on some external field applied to the material. Let's say this is a material, I apply here a field, and this is polarized. So these are two types of questions or two types of scenarios. Both of them are important, and both of them we are going to discuss this lesson. So as a reminder, what we have in mind is some system, a finite system, which has its total charge is zero. So this is a neutral system. And inside we have what we call the polarization field, P. So P is a vector. It is depending on the position, x, y, z. So it's varying here inside in possibly a very complicated way. And this polarization is simply the number of dipoles in a small volume divided by the volume. So at a given point, we have here some small box, and inside this box, let's say we have dipoles in one direction, and the density of dipoles here is big at this point. So this is a function of space. Here it will be low, etc. So this polarization field is changing in time. It's a vector, and it's a field, because by definition, a field is defined by a vector and coordinate in space. But it's not like the electric field. It's in some sense like maybe the charges that create fields in this lesson. So these are these dipoles. They have a direction when they are all oriented in the same direction, and they are responsible for fields, let's say outside here, also inside the matter itself. The question: what is this field? And what we said is, okay, we don't like to deal with vectors and polarization fields. We know something about charges because this is what we were studying in this course. So let us map this problem into a charge picture. So this problem, we said last lesson, is the same. This is meant to be the same amoeba, let's call it. So there are some bound charges and some surface charges. So we map this polarization field to these two charges. One is on the surface and one is inside. One has units of charge per unit surface, sigma. One has units of charge per unit volume. So these are densities and surface densities. They are not the same units. And these two guys, what is the recipe? So the recipe is that sigma B is for the word bound, is P dot N. And what is N? N is a unit vector in this direction orthogonal to the surface. So the surface is this vector is up here this way, and here it's this direction, etc. So along the surface there is a complicated change, possibly if the surface is complicated and not a simple sphere or something like that, or a flat thing. It is changing in space, and then we have this P dot N, while rho B, the bounded charge, is given by minus div p. And you see that the units of sigma is p. That is because dipole has units of charge times distance, right? Because that's one dipole divided by volume. That gives you charge density. And you see that rho b, you take the div here compared to this one, which is p. So the relation between charge on the surface and p, you need to divide by a scale, which is x, and that's the right units at least. And the general picture was like this. And we have this system and a physical picture, and then we say, okay, let us think about these microscopical dipoles, something like this, and then you have another dipole kind of in hand-waving argument like that. So these guys are canceling out, and then you are left, if you continue it this way, you are left here, because the whole material is neutral, you are left here with charge on the surface. And then if you have a change in the polarization along this thing, then first of all, you immediately realize from this and this, using the Gauss theorem, that the integration over this guy, if you integrate over the volume, will give you exactly the charge here. So again, the charges on the surface will be balancing those charges due to here, due to this div p, and this we argued, okay, let's say here we have 3 dipoles, and now we're going to only put 1 dipole here, this will cancel out, and then we are left with some charges instead, if we have a kind of change in the polarization field going down here. Anyway, this was last lesson, we proved this, and one thing we want to do today is to use it. That's one method, and the other method is going to be using a second method, which is using the displacement field. So there are 2 methods to solve these problems, one with some new field. So we have the polarization field, we have the electric field, and now I want to make it 2 is not good, let's make it 3. D, capital D. Did you hear about this D? No. So, okay, you'll hear about something new here. This is D. D is from the word displacement. The word displacement comes from the fact that you are moving something. What are you moving? So let's say the electric field is 0 and all these dipoles are oriented in all kinds of ways, and then you are moving the dipoles in one direction, or you are stretching microscopically the dipoles. That is a kind of displacement. You see it in the microscopical definition of the dipole. You have this displacement. So capital D comes from this displacement. I mean, I'm not saying that these terms are very good, and you'll see that there are many terms here that we put into the theory. So we will look at this displacement vector. So the first thing we want to discuss a little bit is the displacement vector. And why is it useful? Okay, we'll solve some examples with it, and you'll see that it is useful. So again, we'll have 2 types of pictures, one with this new vector D, and one with this picture with the effective charges. And you need to jump between these 2 kind of descriptions. And the idea is the following. Let us look at, now I said before this is no charge, but let us assume that in addition we have what we call free charge. So what is free charge? Let's say I decided I put some ions here. Why do I want to put, how I put them with a chemical bond, I put them there somehow. So in principle, the system can be with the bound charge and with some free charges. So let us see the total effect of these 2 types of charges. Again, the bound charges come from some polarization field, and in addition you have just ordinary charges, which I'm going to call free. So what is div E? What is div E? We know this div E, what we know the Gauss law in the differential form. What is div E? Well, you know what is div E.
Rho total divided by epsilon 0.
Rho total divided by epsilon 0. But now let us write rho total divided by epsilon 0. Okay, you said it and it's so early in the morning. Let's have your famous equation here. But this is PF B divided by epsilon 0. And again, these are the free charges. I'm now working inside the material. These are come from the polarization field. So, but now I realize something. I realize that PP is given by this minus dphi. So I can write this as PF over epsilon minus div P, which is these ones, divided by epsilon 0. Now let us multiply by epsilon 0, and then let us write it like this, div. I'm going to take this P to the other side, so we have epsilon 0 E plus P. This is rho F. Now what I'm going to do now, I'm going to define D, this is the definition of the displacement field, as a combination of the two fields that you are familiar with. One is the electric field and one is the polarization field. And this is a definition. This is just what I'm going to call div D. And there's no approximation here. And what you see here is that div D is equal rho F. So what is this? This is simply, we didn't do too much, right? We just defined something new. And this div D equal rho F, it's essentially the Gauss law, but not for the electric field. For this new displacement field, there is a small difference that we don't divide here by epsilon 0. This is just a matter of notation, while here we had epsilon 0. So this epsilon 0 was defined here in the E, but essentially this is the Gauss differential law for D. So why is this good? In some cases, let us say you have a material, and let's say someone put some charges on the material. Let's say a membrane. You have something inside, and we take some ions and we throw them on top somehow. We know the free charge. This is this free charge. We don't know, let's say, what is inside the material. We need a model or something like that. Or we need to measure, or we don't know, we have no clue. So at least this equation tells you, okay, I can calculate this div D if I know the free charges for some set of problems that I know the free charges. In many cases, we don't even know what are the free charges, but that's a different story. So this is a useful thing because in some cases we can control also the free charges. We can move things. Let's say I have a membrane, I put more charge on top, like an icing of a cake. You put some sugar on top and then you put more or less ions on top, and you are controlling the free charge. So okay, we can calculate or start thinking about calculating this thing. And in some simple problems, this is very useful. I'm not saying it's always useful, but in some cases this field D is useful. So to start, let us do one example to make this more specific, and we will see other examples later. So we have here these two equations, and what I'm going to do as an example, just to settle notations, let us use the simple thing. So we have here a slab. You can think about this as some biological material. Here's a membrane and here's a membrane. Or you can think about it more or less like kind of a, it's not going to be a capacitor, but in the structure it's similar. So this kind of stretches like that. And this is also like that. And I mean, these plates are infinitely long. I'm not going to deal with any finite size effects. So we have three regions, which I call 3, 2, and 1. And this is free space. So this is the vacuum, or the air. Air is nearly the vacuum. It's nearly the same thing. And here we are Z equal D. So this direction is Z. And this is Z equals 0. So the distance between these two slabs is D. And inside we have a polarization field P, which I'll soon specify, which is in the Z direction. So we have some polarization, which is a function of z in principle in the z direction. So, and soon I'll specify this function, but now let us say this is general. So, what we can do in these type of problems is we can say, let's say this is given, this is known. I can say, okay, calculate the charge up here, calculate the div here, and then let's calculate the E. That's method number 1. Now let us also use method number 2 using the D and showing how easy it is to use D. So we are going to use both methods to calculate the E in this simple example, where we're going to exploit the symmetry. So because these things are infinite and P is in this direction, so the electric field is also going to be in the Z direction. There's no reason to prefer one direction on the other here from symmetry, so we are going to exploit this obvious symmetry. So, so first of all, we want to calculate D. So this is going to be method number 1. Calculate, and this is going to be trivial. So again, the question is we know the polarization. What is D and what is E? So, first of all, we assume that this system is neutral, and because I didn't say anything about the free charge, what I mean by this question is that the free charge is simply equal 0. So we know that div D is equal 0. What else do we know? So div D is equal 0. What does it mean about D? What is D? It's a constant. And we also know the direction. It has to be z by the symmetry of the problem. But now we have to determine this d. And I claim it's very easy to do that. How do we do that? We go to infinity, boundary conditions. So when z approaches far away or below plus or minus infinity, then what is the polarization first of all? P is 0. Why P is 0? Actually, P is 0 everywhere here and everywhere here because we have no dipoles there. Then far away, E is equal 0 at infinity. Why? Because this is totally neutral, and if it's neutral, then there's no long-range electric fields. And if P is equal 0 and E is equal 0, then at least at infinity, D is equal 0. And if D is equal 0, then, because D is equal 0 at infinity, div D is equal 0 everywhere. And as this lady said, then it means that D is a constant, that this means D is equal 0 everywhere. So, this is a deliberately simple question. זה לא עובד, אבל אני מבין שהשידור כן עובד. אבל אני לא יכול לדבר איתם. אני לא יודע אם זה דבר רע, כי מגיע להם, הם לא באו לשיעור. לא, אבל אם אתה רוצה טוב. Okay, so we have this D is equal 0. And why we actually solve the problem now, this is very easy. We didn't do any calculation, right? Why is it easy? Because, okay, D is equal 0 in the interesting region. In the interesting region, if D is equal 0, first of all, okay, D is equal 0, and now I know the polarization, so I know E, and we are done. So, what is the E? So, to summarize this method, in this case at least it's very good. So, what is E? Okay, so we have first of all E1 equal E3 equal what? Equal 0. Again, because in these regions D is always 0, P is 0 up there. And then we have E at region 2, just from the polarization, it's minus P divided by epsilon 0, which is means that the field, the polarization field and the electric field are proportional, but with opposite sign.
אף אחד לא נמצא בפגישה, אבל אם מישהו יתחבר זה יעבוד.
למה אמרתי לי? עבודת לי תמיד נכון. תודה. Okay, so this is the solution of this problem. But now we want to gain some more insight. To gain some more insight, we want to look. Let us look at the problem from point of view of the effective charges on the two surfaces and what you have inside. So let us solve something specific. So let us look at this and see if this simple calculation, which is very general for this geometry, works based on the other method, the charge method, the bounded charge method. So let us assume now, that, so I want to define a specific field, which will be the following. Let us assume that P2, remember P1 and P3 is 0, P2 is minus kz in the direction of z. No, without a minus. So we have, in this pedagogical example, what did I do? I added this z here. So div p is not 0, okay? So we have some charges, so to make the problem a little bit interesting, if it would be a constant, what would happen then? You'll have only surface charges. But here we build some material with this non-trivial div. So what is rho b? Well, it's very simple. It's minus div p. Of course, it's only inside the material, and this is simply given by minus k. This k is some number. Someone gives you this number. What is sigma b? So we have two sigma b's, one on d and one on 0. So you see on top, this is something I think you know, the unit vector points upwards outside the material, and then here we see that this is rho kd multiplied by n in z direction. What is the sigma b downstairs?
0.
It is 0 because the polarization is 0. So here are the effective charges. So the effective charges that we have here are 0 on the surface, kd, and minus k. This is rho b. This is sigma d. These are the problem, and we can solve this problem. We can solve this problem quite easily because we can create here Gauss boxes, and this is a simple problem. So what we will do is we will check whether or not this solution gives you the correct answer. So what I'm going to use is actually the integral Gauss law. Create some Gauss boxes. So let us, first of all, you see here the charge is plus and inside it's minus. And this is consistent with what we said before, that the total charge is 0. This comes from the difference in the sign, and soon you can nearly see that the total charge is the same, is 0. But okay, if you don't see it, we will show it to you. And this is first sanity check. Secondly, there are jumps in the electric field, right? So the electric field is this guy. So there is a jump in the electric field here. Is there a jump in the electric field downstairs? There's no jump. Why there's no jump? Because E2 is minus P. It's 0 there. So there is no jump from here to down here, because remember down here the electric field is 0. Does this make sense? It makes sense. Why? Why does it make sense? Why is it obvious that it should not jump?
The charge density.
Exactly. The charge density here is 0. So remember the boundary conditions for electric field is that if you have a flat surface, or even not a flat surface, some surface, you have an electric field pointing in this direction and the other one in the opposite direction, the jump in the field is equal to the charge density at this particular point. So here the charge density is 0, so here we get, you know, a consistent description. Let us look now at it's two boxes. So we have this thing, and we have, let's call this box, I call it a gauge box. I don't know if this is a good name. So this is a theoretical box that I built here. And what do we know? We know that the integral over the fluxes of the electric field that coming out of this box is equal to the total charge enclosed divided by epsilon 0. This is what you learn, and that we learned it in our course, and I think you know it for a long time. So let us see for this box that it kind of works. So for that I need to define a new length. Is this length important? The answer is not really, but I needed to prove the theory. This is the length z. So z is something between 0 and d. D is the width here. So first of all, what does Gauss tells us? It tells that on this surface of box, let's call it A, EDA, this is Q enclosed. Q enclosed is in the box divided by epsilon 0. So what is this EDA? So let's just think about this for a second. We have this box A, and okay, in the middle we have the plate. Where is the flux coming out of? The flux is not coming from the two sides or the four sides, simply because the direction of the field is in the z direction. Is it coming in here, downstairs here? No, because here E is equal 0. So the only place where you have flux is up here, because D is somewhere on top. This is the only where the flux is going out. And we know the field because we calculated it here. Here it is. So what is this thing? Let's call this area on top, let's call it SA. And the point of this thing is that the flux will of course change when we make SA bigger, bigger, more flux. But on the other hand, also the enclosed charge will become bigger. And this is the bulk charge, the bounded charge. So okay, so what is this EDA? On the one hand, this is okay. What is the field? The field was the following. I'm using here the field KZ prime because this is this equation. So KZ
And at that level you do not know the field yet. You need to calculate.
Just a second. S0 divided by epsilon 0. This is minus. Yeah. So again, the P2 is KZ, then E is minus, maybe I should write it down. So what is E? Is minus KZ in the Z direction from that equation. So I just write here for this side the flux on top only. It's the field
divided by epsilon 0.
What?
E divided by epsilon 0. No?
Yes, sure. Yes, divided by epsilon 0. Thank you. And what is so this is this integral EDA. And now I want to calculate question mark Q enclosed. So now I'm just checking, but we could have started here, of course. We could have gone the opposite way. And this is equal to rho B. Now I need the volume where the charges are. The charges are up here, not down here. So I need Z times S A. That is the volume of the box inside the material, and that is the total charge. But what is this is Z, but you see immediately what is this guy. This is minus K, because this is div P, this is minus K. And then I need to, yeah, of course, when I need to divide here by epsilon 0, this is this epsilon 0, and you see that what I have on the two sides of the equation is the same. So the total charge here inside is the same as the flux that is going on the top, and this, it means 0 equals 0, and then we are very happy and everything is good. So now we can do another box if we want. This is this box. This was box A, and now we'll have box B. Again, this is a theoretical box. And now I want to calculate the integral of E dA. So we have fluxes in principle from all the sides of the box, but the field is only in this way. And here E is equal to 0. And here E is equal to 0 because, again, D is equal to 0 and P is equal to 0. What does it mean? This guy is 0. So the question is simple. If the box is beyond this size, this distance D, is the total charge inside 0 or not? We expect it is 0 because otherwise there would be free charges. There will be the total system will be not neutral. And then it's very easy to show that what is this? We just need to go to the dictionary up here and we need to calculate this. So if I call this top SB, the surface of B, this is just the surface. So we have SB times D. This is the volume of the box inside the material, only this part. What we have here is not important because there's no charge there. And then we need the charge, which is minus K. The charge density. This is rho B. Is that enough? No, because we also have charges on top. This is the charge density that we have on top here. What is that? KD. That is sigma on the surface multiplied by what? By SB. And that is indeed equal 0, so I'm very happy the total charge is 0. Again, because we saw it already here more or less, the surface charge is KD, so it depends on D, the surface, effective surface charge, it depends on D, and then if I take here a slab, it will be KD multiplied by the slab, this is what I wrote, KD SB. Some box, it doesn't matter what it is. And then the other charge which comes from inside, you need also the height D and SB because this K is the charge density. So I multiply by volume and then you get 0 equals 0 and everything is working fine. So here I showed you these two methods and you can argue, okay, this is a very simple problem, but we always solve only simple problems. And the two methods give you the same results as expected, and one of them gives you more insight because it gives you the charges. The other one may be easier because what we did here at the beginning with this D, we did practically nothing. We just said div D is equal to 0, and then everything was solved without looking at these charges. Okay, so we have these two methods in mind, and you need to choose your poison when you solve all kinds of problems. But now we are going to start addressing the following question. Okay, here I gave you the polarization field as a present, but the nature and real physics is not so nice, or actually, in fact, it's beautiful, because in many cases we don't know what is P. Why do I say it's beautiful? Because there are many problems like this in physics. Like, what is the potential between some objects or something like that? Because, you know, if great people would solve everything, there would be nothing for you guys to do, right? So in many real systems, the question is, what is damn P? What is it? We don't know. And then ordinary people like me and you come and say, okay, for this case, this is P, for that case, that is P, and then we go to conferences and we give you some option to do some real research. Otherwise, everything will be ended. It's not like that at all, because we are left in some bubble of, we don't know what is the charges, what are the polarization fields, but there is a method based on what I'm going to call linear response. That is when the external fields are not too strong, the electric fields that induce dipoles. So I think about some material and I add some electric field. These materials are called linear materials. Many of them, many systems are linear. In fact, most systems are linear, provided that the electric field that we apply on them is not too strong. So we can always work with not so strong, give you a small hit in, not a big thing. Of course, it's not that the nonlinear systems are not interesting, but at least we can handle the linear systems. And what is, so we are going to talk about linear dielectric material. And again, we want to have a method where we don't know P, we don't control it. We also don't control E inside the material. But what we can control in laboratory is if I have a chunk here, I can control E far away, apply some electric field in this direction, and then, okay, what will happen? So that's the essential question. So the idea, roughly speaking, is I have an E, and then I have some material here, and what will happen to the dipoles? We already said, microscopically, we said last lesson, what did we say? What do dipoles like to do in material? They like to align. It's like a magnetic field that magnetic moments cause an alignment. Now, how exactly they align? Well, that depends on the material. It will depend on many things, like temperature, pressure, because also these dipoles may be interacting. It's a super complicated thing, and we are not going to discuss it at all. That would be microscopical theories. We are now on a macroscopical theory, not the details of the microscopics. And then we just say, what is a linear material? We say that P, this is not alpha, oops, this is proportional to, and soon we'll add the proportionality constants to E. And this means also, because of the definition, that D is proportional to E. What is the coefficients here? We'll soon define them, but this depends on material, temperature, and all kinds of junk. So the idea here, I apply a field, and then you have this polarization field in the same direction here as the field. And remember what we said last lesson, we have all these dipoles, and in a solid, they are all oriented in a kind of random ways. So they cancel each out, even in a small box. And then you apply a field, they are all directing in one direction. Or more correctly, more of them are in this direction. It could be that they are not really all aligned, but a majority is aligned, or some epsilon of them are aligned. But this is a macroscopical field. And then the proportionality will depend on some of them alignment. Okay, so this is more or less the microscopical picture. And you go to the lab, you don't know what is inside, but you can apply this E, and then you can use these assumptions and make predictions, and then you can measure them. And the payment you need to do is you need to say, what is the proportionality here? This proportionality is a phenomenological number that we add to the theory. Phenomenological number means material 1 at temperature 1, at pressure 1 has one constant. At a different temperature, it will have a different constant. So this is something that you measure. You don't know what it is, but you add it to the theory. And it's not something basic, as let's say Coulomb's law, but it is something super useful and found in every material. So you can go to tables, and you can find material 1 has some proportionality, material B, a different and you can vary temperature, and you can simply measure this for different materials, and then you go to you go to some. It used to be books, but now you find it on the internet, and then you can say something about this thing. So. So if this is the field, just the convention is that the dipoles are defined from minus to plus. So this is the P. And okay, so another way to put it, let's do it again. Let's say E equals 0. We have all kinds of dipoles in all kinds of directions. Let's plot it like that. So the experimentalist has no E, then it's turned on. There's no polarization. Sorry, there's no E, there's no polarization. What I mean by no polarization, it's not that there's no dipoles, but they are all oriented in different directions. They cancel out. So the macroscopic P is 0, and then if E is not equal 0, then we have some P. Majority of them go up, and here we have P. So here I mean that the P is going to point up here, and here P is not equal to 0. That's the general picture. Okay, so let us see where this linear theory brings us. And to define things, we need to define a property of the material, that the specific one that we have here. And this is going to be defined by chi E. E. So now I just made the statement slightly more precise. Instead of P proportional to E, I give here this epsilon 0 is a constant, universal, basic constant. Chi E is a material constant that varies with many parameters. And why is it called chi? Chi is called, what is it called? It's called the small the E here is for the word electric. There is also a similar constant for magnetic fields, and this chi is called electric susceptibility. Very difficult word. Electric susceptibility. Susceptible means, let's say, if you flatter me to get a better grade, and then you can say, I'm not influenced by this flattering, so I'm not susceptible to your flattering. That's what means. Someone who can respond, or a material that can respond in some way. This is the meaning. If you respond easily to something, you say you are susceptible to influences, political influences, whatever. This is the meaning of this word. This is how you can memorize it. So we are going to assume this thing. However, this is not what the only thing that is done. Chi is very useful, but many times we define D, because what is D? D, we add it here. It's epsilon 0 E plus P. So it's epsilon 0 1 M plus chi E times E. This is just from the definition. And then this, annoyingly or not, I think it's not annoying, but I just got used to it, maybe you think it's annoying, is defined like this. With this epsilon here. This epsilon here, epsilon 0 has units, you know this. Epsilon is a dimensionless thing. Griffith signals this epsilon with an epsilon r. R from the word relative. It's called the relative permittivity. Oh, so many names. It's like doctors. So this is called electric permittivity. And you see the difference. Why do we have two definitions? Because in some sense P is important because that's the polarization field. But we already saw that D is very useful in the equations, right? Because D is related to the free charge. So D, when you calculate things, you usually, or many times, you first calculate D. And that's why you want a definition like this. So there is some reason for this. And what is this epsilon? You see immediately this epsilon is 1 plus chi e, so it's nothing unusual. What is the meaning of the 1? When is chi e equals 0? When is chi equals 0? The simplest. When you are in vacuum or in air, more or less, there is no material. If there's no material, you apply electric field, you don't polarize anything because there's nothing. If there's nothing, you can do nothing. Great sentence. So anyway, so for vacuum chi e, we expect to be 0. So you see, if it's 1, if chi is 0, this epsilon is like saying, oh, your material is vacuum. So this epsilon is relative to the vacuum, this addition. So if it's 1.1, it's more than the vacuum by 10%, right, or something like that. So this is this thing, and then okay, if I take the definitions back here, so I have here P, I can reverse it, then I have epsilon 0, then this chi e is epsilon minus 1 times E. And again, Griffiths used ER, R for relative. So this is chi E. Okay, so we can choose one of them, and we will choose epsilon, and the relative one, when you subtract the 1. So material, this I guess is in room temperature, normal pressure, nothing, normal densities more or less, that you get an idea. So if I have vacuum, I mentioned this is 1. Yeah, because then chi is 0. If it's air, you expect that it is close to 1, right? It's nearly 1. If you want to have a number, it's 1.0054. Some normal conditions. And then the nice, what is the nice ingredient in nature that has a big epsilon, you know?
Water.
It's water. Water is very, very weird. But the water, which is the most important one, is the most susceptible. So it's very, very polarized. And let's say salt, NaCl, which is also pretty, this is something like 5.9. So you get ideas, more or less. I don't know what exactly they mean by salt, water with salt, or no, it's just salt. So this number 80 is pretty big, which means that water, because of the, it's not trivial, but because of the high polarizability of the water molecule, because it looks like this V and the charges are down here and on top there, it has a big dipole. So anyway, it responds like this very easily. It's very susceptible to external influences, which means you can play with it with the external fields kind of nicely. Water has many, many very weird properties. This is one of them. Okay, so now we're going to solve the simplest thing, just to get a feeling. Yeah, so let us say we have a charge Q. I'm going to call it Q free. Remember, Q free, we had two types of charges, the bounded charges and the free charges. So what is this charge? Let's say I put an ion or some small bead with charge on top. I put it in water. So there's water surrounding it. There's only one charge. And I want to know what is the corresponding Coulomb's law. That's as simple as that. So I want to stand here. Some distance away from this ion. And I want to know what will be the electric field that I will feel here. So the general picture is like this. What will happen? QF. So let's say it's positive. What will happen? So I'm going to plot here some imaginative radius where the water is. And what will the water do? It has we'll think about it as dipole, so we have minus plus, minus plus, minus plus, plus, minus, minus plus, minus plus. So what is happening here? The dipoles, microscopically more or less, have a minus and a plus head, right? And this is a positive charge. So what do these guys like to do? They like to go and point to the positive charge. So you see here more minus than plus, minus than plus. Now, these spheres that I built, there's another sphere here. The density on these spheres is changing, and then you have some polarization gradient, but you have a polarization. And what will happen if I look kind of here in the middle, at least in this kind of schematics? What will be the effect of these charges? So the negative charges are coming closer to the positive charge. So what will happen to the effective charge, the effective positive charge? When you imagine, it will go down. Effectively, it will go down. But how much will go down? Well, that has to be related to this epsilon here. And this is what we are going to find. So this is called screening effect. You have the material around you. It kind of screens you. And now, a simple exercise that we're going to do now, we will be able to calculate this, not microscopically, because we don't look at all the small details here, but just using these schemes, assuming that the system is linear, that the response is linear, which you can doubt very close because the electric fields are very strong, but so maybe you were looking far away. Obviously, very close to this charge, this is all wrong, because very close, let's say the distance between the charge, if the charge is microscopic like an electron, I'm not thinking about that, but you have a gap, right? So in the middle, there's no polarization at all. I'm not talking about the smaller scales here, but some bigger scales, like far away from this. After you have, let's say, bigger than the scale of the dipole. The dipole is a few Armstrong, and I'm looking at larger scales. So, okay. So what is this? And again, this is super simple, but also a little bit deceiving because it's so simple. And so you can say, oh, everything is so simple. But let us do this. So we have, remember what we have. We have div d equal rho free, right? Div d equal rho free. Now we are going to write it, but not in this form. Immediately we know from electrostatics, from this course, instead of div d equal rho f, because it's boring, let us write it in a kind of a different way, with an integral. So we know that this is the same thing as what we had before, qf. Again, Q3, the charge of this ion, the charge of this macro sphere, or whatever it is. And then immediately, what is D? So I hope you understand how I got this one. Yeah, good. Thank you. So immediately I know from here what is the answer to this, because, okay, let's think about this as a point charge. So immediately we see here Coulomb's law. So okay, what is D? It's trivial. D is QF 4 pi r squared. This is the famous r squared of the Coulomb law, and in the direction r, which you all understand what I mean, here is the QF, and this is the direction of the D. And okay, it's not exactly the same as Coulomb law. Why is it not exactly the same? Because the epsilon 0 is missing, but this is just because of our definition. We didn't define by epsilon 0, but everyone can see this is the same as Coulomb's law, and D is as usual. But now what, okay, and up till now actually there is no assumption. Not linear and not linear, I didn't assume anything here. Now we are going to put in the assumption of linearity of the material, and if I know D, then I know E, one of the equations here, this one. And then, so let us write it down. So now I'm adding this assumption, linear material. Then I know that d is equal epsilon E. And from here I know E, which is Q 4 pi epsilon 0 R squared. And the new thing here is, of course, this ER, this E. This is 0. And you see what happens is exactly what I already told you. Let's say we are in water, this number is 80, so this is the Coulomb's field, but reduced by a factor of 80, and that's it. So, okay, it all looks super trivial, and you might be tempted at this stage, okay, all you need to do is, in linear material, you solve the same as usual electrostatic, but replace E0 by E0 times E. It looks like this. Is this correct? The question is when it's not correct. Many times it is correct, and that's many times you say, okay, it's very simple, but it's not. There is a difference. Can anyone say, maybe someone read about this? When will you see differences between the field D and the electrostatic field? When they are not the same, even though they are proportional.
The rotor.
What? Yeah, exactly. The rotor comes in. So maybe one guy read a little bit, or you just now, you read it. You know it from yesterday. That's a long time ago. Okay, so that's very good. So what we are using here is Gauss law, but we're not using rotor E equals 0 or rotor D equals 0. I'm not saying what is rotor D still, which means the following question. Can we write a potential V, but not for E, for D? Because they look the same. The answer is, no one promises you in general that rotor D is equal to 0. And this creates, in special sets of problem that, nasty teachers like me like to give in exams, you fall on this because you don't notice the differences. And we will discuss a little bit this difference now. So let us just emphasize this point in set of equations. So what looks similar and translates is the Gauss law. And let us summarize a bit. So always div E, this is like a law of nature if you want, is rho free plus rho B divided by epsilon 0. Div D is equal rho free. These two equations are general always. In linear material, E, and then div E, and then div E. Because it's a linear material, div E is equal to rho free epsilon epsilon, the relative 1. Here I'm using the fact this is only for linear material, which, this is what I said before, you just need to replace E by epsilon, E0 by epsilon. I use here the definition of D and then divided by epsilon 0. So because div D is the rho free and then E is proportional to D, then I just divided here. This is from where this equation. But the boundary conditions are not trivial. Many times boundary conditions are not trivial. Okay, so this was a summary or a mid-class summary. Okay, so now let us continue and go and discuss the other law, the elephant in the room. So this is again, this is in a linear material. But now let us remember the following. By definition, we have this, but let us copy this equation. E plus P. And therefore, the rotor of D is equal epsilon rotor of E. But what is the rotor of E in electrostatics? It's 0 plus rotor of P. So we have dd equal rho P. Now, in the examples I gave you so far, I cooked special examples where rotor P was 0. For example, in the linear system where you have QF, the fields are, let's say, the electric field, but also D. They are like this, right? In this example. So here the rotor of D is equal 0, and also the rotor of P is equal 0 because of symmetry, because there's no imposing on the boundary of some rotor or anything, and this is what we got, and this is what we maybe assumed. But there are other problems where this is not the case. I mean, it's not a general thing that the rotor P is equal 0, and then you are going to have some problem with rotor D. But if, I'm going to say it differently, if rotor P is equal 0, then D is just like usual electrostatics with replace E0 with E0 times ER, right? So those cases are simple. So let us look at the boundary condition. Now the boundary condition, I think and hope you add in, we didn't discuss boundary conditions, I think, in the class, but you did discuss them in homework, and you also read about them. And I'm talking about boundary conditions just for electric field with no polarization. This is something you know, I hope you know, but I'll remind you, you see, as a favor. So we'll soon remind you what are these, and then we'll clean up the mess. So, okay, so first of all, div D is equal to rho F, rho free, we showed this already. And now let us remind ourselves what happens for E. For E. No P. This is a reminder. I'm reminding you of the rules so that we can modify them when we have polarization. Okay, so what do we call this? Let us remind ourselves. We have Gauss law, and then we have div E is equal rho in general. This is always correct, divided by epsilon 0. Rho can be also from polarization, but some rho. From here, we can write this as an integral form, right? EdA is equal Q enclosed divided by epsilon 0. And then there is this rotary is equal 0 in electrostatics. So this, we can call it no potential theorem. I mean potential theorem, but there exists a potential. And then we get from here, in the integral form, we get, this is now a line integral, EdL equals 0. When we close a line, so we do an integral over a line with an electric field, we close it. This is the same thing, that there's no work doing along this thing. This is what we know. Okay, now we want to remind ourselves what is the meaning of these equations when we go to boundary conditions. And then we want to correct them because of this rotor thing for D. B. So what do we do? So we have some surface. On this surface we have some charge density, sigma. And then what we are interested in the following: E1 parallel, E1, not, this is not parallel, this is perpendicular. E1, so this is material, this is part 1, and this is the boundary condition. Here is 2, and then here I have E2 parallel. It's parallel to the surface, right? And I'm showing here the directions that I assume. Of course, if the field is minus, it will be in the opposite sign. So this is E2 perpendicular to the surface. So at each point on the surface there is an electric field, which generally is in some angle, and it has two components, and these are the two components. Of course, this surface doesn't have to be flat, but it's locally flat. So if later on this goes down, I don't care. I can build this same thing. This is just the term perpendicular just means perpendicular to the normal of the surface at local point. So what did we say? We said the following. So from rotor E equals 0, which is again the law that we have to change soon because of this. Then what we did, we said, okay, this is the surface, and then we are going to use this one, right? The line integral, and we do it on a box. So we do an integration I like to point it like a smeared box. Of course, this is going to be infinitesimal, and then we do the integral of the electric field, which is parallel. Then we go back, electric field down here, and all this integral from on the top and the bottom has to be equal 0, and that means that from here we get that these two fields have to be the same. E1 parallel equals E2 parallel. And then to calculate these perpendicular components, we use the second law, which is Gauss, this one. And what we do, Gauss law, so what we do is we build a small box here. And we look at the fluxes up here and up there. And we use the fact that these two guys are the same, so they will so the fluxes coming in here and there will be the same, and now we need to care only about the fluxes from the top and the bottom. And then you have inside here, you have some sigma. So what is the charge inside? It's this sigma multiplied by this area that we have on top. Call it S something. It will cancel out because this S is going to also be proportional to the fluxes. And from here what we get is that E1 plus minus E2 perpendicular is equal sigma divided by epsilon 0. So these are the two usual boundary conditions that are derived from these basic laws. So now what will change? So first of all, so let us look now. Now the question is simple. We say what happens to E, but what we care about is what happens to D. And what will change here? Well, let us look at this thing, if you can. Let's look at this law. Will this change? The answer is yes, because rotor D is not equal 0 in principle. So this one will change. Will this change? No, because the equation for D is the same as this Gauss law. Nothing will change except for some epsilon 0. Is that clear? So that is the general strategy. This law more or less doesn't change. So yeah. So because so I don't know where I have it somewhere. Here we have it here. So because, so the question is, what are boundaries, boundary conditions for D? So Gauss law more or less unchanged. Why? Because div D equal rho free. So nothing changed in Gauss law, which means that, except for this epsilon 0, this means that if now I have D1 parallel, D2 parallel, D2 perpendicular, and that means that D1 plus minus D2 plus perpendicular components is equal to sigma free, and there's no epsilon 0 here. This comes from the definition. And what happens to the other law that we have? So this is unchanged, and what happens to this law? And it's also kind of simple because what is happening here? The other law, we have rotor D is equal rotor P, which means that the jump in D will depend on if you have a jump in P. Because from here I can immediately see that ddl is equal integral. Again, why is this correct? Because rotor E is 0 is equal PDL. So if you want P minus ddl is like the E, and the jump is like that, and that means that D1 plus minus D2 plus is equal P parallel minus P2 parallel. So this is the boundary condition. If these P1 and P2 are equal 0, then we are done, and then the problem for D is actually the same like E. But if not, then we have a jump. If there is a jump in the polarization parallel to the surface, something here and something there, this happened. What happened in our first examples? We had a slab, for example, and there was a Z. So there was no parallel polarization in this way. Remember? I always give you simple things to solve, to trick you to think everything is easy. Because it was in that way. If I add something in that way, and up here I have a vacuum, so there is a jump in the P parallel. So if I have a polarization in that way, then there will be a jump, and then you need to consider it when you do the boundary condition. Okay, so we saw that there is some differences, and now let us solve one simple example. Which will wrap this up. Before we had an example, it was not a linear system, and now we're going to use a linear system and solve an example of a linear system. So let's see what happens. Yeah, so what I'm going to do is I'm going to solve Okay, so what I'm going to solve is we have a linear system, which means that it responds to the electric field linearly. The polarization is linear in E, is in a field epsilon 0, E0. This is the electric field E0. This is an electric field which is far from the system. Which, and more specifically, I have these infinite slabs like before. And I apply here an electric field in the z direction. So E0 is perpendicular to z. And because of the symmetry, all the polarization fields will be in this direction. It's going to be a relatively simple problem. So what do we have here physically? Here inside we have some P. But what kind of polarization field? Before it was a given polarization field. Now it is an induced polarization field. Induced. What do I mean by induced? If this electric field is 0, then that polarization field is also 0. By applying the electric field, we induce the directionality of the dipoles in one direction, and you create this P. So now we don't know what is this P, but this P is related to this epsilon 0, this E0 field far away that the experimentalists can control. So the nice thing about these experiments, you can make E0 slightly bigger. You cannot make it too big in order not to break the linearity of the system. And you can verify this for a set of E0s, at least in principle. So the question is, what is D and what is P in this case? And we will do it more or less in two different methods. So here what I mean is, here we have, let's say, air. And for physicists, air is vacuum. I write air because you can imagine a real physical system in the laboratory like this. And here inside you have some material, let's say water, and you apply this E0. Okay, the questions are, of course, what is D? Now we are asking what is P. If we know D and P, we know E everywhere. What is rho B? What is sigma B? And essentially, yeah, these are the questions. So, what is E? This is going to be... okay, so again, let us start with, what would we start with? What is the easiest one to start with, in your opinion? It's like before. It's actually D. That's why we introduced this strange field. What is this D again? I repeat myself. It's like E, the electric field, plus polarization field. So from physical contact, maybe you're not interested in this, but now we are solving the problem we first solved for D. Why is it easier? Because there's no free charges in this problem. I didn't say this, but there's no free charges. No free charges. So at the beginning, you should always find the easiest object, and the easiest object is D, and then, okay, then we can stop and think. So, what is the, first of all, let us make the claim. What would the claim? Okay, so I have here regions. This down here is 1, this is region 2, and this is region 3, and this distance is D. So the first claim, and we will show this, it's very easy, is that in region 1 and in region 3, this is simply a constant. Remember the slides, the field E0 is given by the experimentalists far away. So this is not a totally trivial statement, but it's nearly trivial. Yeah, so the experimentalist is not working here. He applies an electric field far away and he measures it down at minus infinity. But we claim that this is the case. How do I know this?
There is no polarization outside.
So first of all, exactly, there's no polarization outside. P1 equal P3 is equal 0. And that's before div D is equal 0. What is D then?
E.
Exactly. So D is nearly E. The polarization far away at infinity. So the way I think about it is, let's look at Z to infinity, far away, where the boundary condition is given. We know that P is equal 0. And then we know that D is epsilon times E0. Again, because P is equal 0. There's no material and no polarization. Now, because div D is 0, and so it's a constant, and it's a constant given by this number, at infinity it has to be like this everywhere. So D is equal epsilon E0. This comes from here, and the boundary condition. But the thing is everywhere. If D is like this, and P is equal 0, then obviously E1 and E3 is E0. Okay, is that clear? We didn't do much. It's very easy actually. And is it clear or not? Well, that's clear. Okay, it's both too early and too late together, so it's a very bad mixture. So okay, so we know D. So now what is wait. Yeah, okay. So now all we care about now is region number 2, which is where the material is. What is the relation? And up till now, I didn't use linearity. This is without linearity, what I said up till now. Now we can apply linear conditions. And that is, if it's a linear thing, so if it's a linear material, then E epsilon 0 E2. So again, here I'm using the linearity because I'm introducing this epsilon. This is a property of the material itself. Some epsilon, we said 80 for water, for example. Now, what do I know in these two things? I know D2, because div D is equal 0, and this D is everywhere. This is, wait, this D, no, this, I think I missed something. This is with an epsilon here. It's not the E. Only here I have the epsilon. Up to now there was no epsilon. Here I had epsilon 0. That's why Griffiths called it epsilon R, so not to make these type of mistakes. So now I know, but I know what is D, because I know D again everywhere. So what is D? D is epsilon 0 times E0, the field far away, is equal epsilon 0 E2. So E2 is epsilon E0, the field that I control. This is the known in the problem. It's an external thing divided by epsilon. It's in the z direction. So what is the polarization? Let us write it. We can write it from this equation. I know D and I know E, so I know the polarization. as usual, from the definitions. So I can write down immediately in region 2 what I know D2, I know E2, and then I immediately can write down the polarization. And okay, this is easy. I'm going to write it down. It's easy to show that it's epsilon minus 1 divided by epsilon 0 E. And you immediately see that if epsilon would be 1, like if the material itself would be vacuum, this is equal 0. And this comes from the definition. Again, I repeat myself. I know E2, I know D2, then I can easily calculate P2.
Why divided by epsilon?
You want me to do this? Let us check.
Say that P is epsilon 0, epsilon r minus 1.
Let us see.
Epsilon 0 high E. Shouldn't it?
So we have okay. So we have these equations for D and E, and then what we are going to use is simply the definition of P that I now. Okay, so P is D minus epsilon 0 E. So what is D? We just plug it in here. We have E epsilon 0. No, D, where is D? I didn't write down D. Yeah, D is over there. D is epsilon 0 times E0. This is the problem. This was what confused me. This is epsilon 0, the external field. I forgot to write the 0. That's what made you confused. You're absolutely right, correct. So these are the external field. This is the given in the problem, not the E. We don't know what's the E from the start. We know we control this E0. So this was the mistake. So, but let us write it down. So it's epsilon 0 times E0. This is this one. And then we have here minus epsilon 0. The E is, this is divided by E. And then I just write it as epsilon 0 outside. And then I write it as 1 minus 1 over epsilon E0, right? You see, E divided by E is 1. 1 minus epsilon is this one. Okay, so the important thing is that you have it here. So this is a simple exercise to prove that this is the P2. But now we want to go back and reflect a little bit. And we want to say something, okay, what can we say about the charges, effective charges? Does it work? So this is a nice method. Let's say we use this method. And now we can check if we can check it. We can check the solution, which is always good, because if we made a mistake, then we can find a mistake on the way. So let us let us summarize what we got. We got here P equals 0 because there's no material. Here P equals 0 because there's no material. Here there is a P, which is this expression I'm just copying. E0 times E0 in the Z direction. Here I have E0. This is the electric field. Here I have E0 over epsilon. And here I have E0, all of them in the Z direction. So I wrote it the polarization, I wrote it the electric field, and of course the D you can easily calculate. It's just a constant, that's why I don't plot it here. So now, from this description, I can find the charges. And if I can find the charges, I can then recalculate this again and check that my results are correct, consistent. So what is the effective charge picture? So here what we get is a constant P. So what is the charges inside, what we call rho P? It's 0 because there's no, the div of this P is equal 0, so this is 0. Now we have here something which I'm going to call bound charge. This is this bound at D, and there is C bound at 0. Now again, we apply this this normal up and normal down. So what this means is that the charges on top will be plus and the charges on the bottom will be minus. This is of course also a sanity check because this means that the total charge of this system, the effective charge, the bounded charge is 0. So what is this charge? We just need to copy this. This is epsilon minus 1 over epsilon. Epsilon 0. E0. Let's put it in absolute value. I'm thinking about epsilon, this E0 as positive. It's not a vector because now we are dealing with this guy. And here we have epsilon minus 1 over epsilon with a minus sign, epsilon 0, absolute value of the electric field. So this external field that we applied from far away induces charges, effective charges on the top. The stronger the field, the more charges. Here you have minus charges, here you have plus charges, and you control them by the strength of the electric field. There is no mystery here because the total charge is 0, so it's not that we created charges. So some of them went more to the surface up here and some down here because of the electric field that comes from downstairs. So now we can use this method and so first of all, you can check, I'm not going to do this, that, so check number 1, jump in E. Which direction is the jump in E? It's not in the parallel direction, everything is in the Z direction. The jump in E, and we know what is the E because we have this thing, is given by this sigma BD. And you see it jumps here and it jumps here, it jumps here and it jumps here. Here it jumps in, because epsilon is bigger than 1, so it's, let's say it's 80. So here it's small, here it's big. So you make a jump, you have some positive charges up here, and here you have negative charges. And the jumps here and here are the same, right? And you see that also the charges on top and the bottom are the same, except for the sign. And that the reason is, again, consistent with this boundary condition, that these jumps have to be the same. And if you calculate these differences, you'll get this epsilon. You can more or less see it. You see 1 over epsilon and 1. This corresponds to 1 and 1 over epsilon. It's very easy to show this this check. But we can also do, for example, we can add again a Gauss box. What is the easiest Gauss box that you should? The easiest Gauss box, you know, let's say you are in an exam, you want to quickly check your result. So, let's say you don't have time because the exam is going to finish soon. So the most simplest thing to do would be to put a box like this. Why is this the simplest thing? So what is the fluxes here? The fluxes can come only from here and here. Are there fluxes here? Yeah. On top, on the bottom? Yeah. Only on the bottom and only on the top? Yeah, because here is my field. This is epsilon Z, this is E0 in the Z direction. And what is it up here? It's E0 also in the Z direction. So what is happening here? There is a flux here, which is proportional to the size of this surface, a flux up here. but they cancel out exactly because electric field here and electric field here are the same, and then what we get here, the total over the box, let's call it A, EDA, there's no fluxes on the zero, and that should be equal to what? To Q enclosed. But what is Q enclosed? Here I have positive charges with some charge density, and here I have negative charges with the same charge density. This is this guy and this guy. So what is the total charge inside? It's zero. Because what is the charge? The charge is this sigma B multiplied by this surface area, call it SA. And here I have the charge multiplied by the surface area, which is the same thing with a different sign. And indeed, this is equal to sigma B times, let's call it SA plus at 0, sigma B at D times A, because they are the minus 1 over that equals 0. So not only the total charge is 0 now, obviously, because the system is not charged, but this also gives the symmetry between this E0 up here and E0 up here. It has to be the same in order to cancel the fluxes in this box. And this is indeed what we found here. And then you can do the same, but you can do it now inside the box. You can generate this check. And now it will be different. Why will it be different? So if I now do this box like this, so we have this charge density sigma B0. We have this surface area here. And we can call this Z, while this one is D. And now, what is the charge inside the box? It's not related to the charge on top here, it's just related to the charge density down here, which is this one. And is there a flux here? So the answer is yes, there is a flux now, because here we have this E0, but inside we have E0 over epsilon. So the flux coming from the bottom and the flux going out from the top are not the same, which is a good thing, because then the total charge inside is something. So here I have E0, and here I have epsilon 0 over E. Yeah. So what will we get here? Now we will check the numbers. Symbols. So EDA, this is on this box. This is equal to the surface of A, and one of them is with a plus and the other one with a minus. So this one is with a plus, actually. Epsilon 0 divided by epsilon minus E0. E0 is just the magnitude. And then the question is this equal to Q enclosed, which I need to divide by epsilon 0. Q enclosed is simply sigma B on 0 multiplied by SA divided by epsilon 0. And you see immediately that SA is cancelled, which is as usual. And sigma B, we have it here. So okay, this guy is equal EF E0 1 over epsilon minus 1. This guy is equal to what do we have here? We have, you see here, epsilon over epsilon minus, so I'll write it like this, minus 1 like this guy, I'm changing, and then you have 1 over epsilon, and then I have epsilon 0 divided by epsilon 0. This comes here from this famous epsilon 0, so they cancel, multiplied by E0. So we get 0 equals 0, and then we are all happy. So everything works well. The total, again, what I try to emphasize here that there are two methods working simultaneously, one with the vector potential vector D, this displacement vector. You may like this method or you may dislike it. It has advantage because if you understand the boundary conditions, it's usually very, at least in simple problems, it's relatively simple. The disadvantage, in my opinion, is that you don't see the effective charges, and if you don't see the effective charges, you may not understand the real physics. But if you want to solve things, it's a good thing. So both these methods are useful. Sometimes, again, as usual in the physics, sometimes method 1 is useful, sometimes method 2 is useful, and you need to handle both of them. Okay, so here we're going to end. You will see that this displacement vector D, there is something similar for magnetic fields later in matter. This is related to the usual magnetic field, which is usually called B, and the effective, when you have matter, it's called capital H. So this is not only limited to electric field. We will talk a little bit about magnetic field also, but because there are a lot of similarities, this will be more condensed. So in the next lessons, what we're going to do is we're going to quickly discuss magnetic fields. This was done already in the homework lessons. And what we had here is chapter number 4. So magnetic fields is chapter number 5. I will focus mainly on the end of the chapter, which is the vector potential and the multiple expansion for magnetic fields, static magnetic fields. Some of this material you already saw, so please read it because we'll try and move quickly. For example, Biot-Savart. You should know this law, Biot-Savart. You should know Lorentz force, all these things. Div B equals 0, rotor B. What are the different definitions of the currents? J, there's a current in as a density current. There is a current on a surface, usually with K. There is a current on a line, which is, which letter? On a line, in a line, a current in a line. This is a high school, I. So there's I, there's K, there's J. I'm mentioning this not because it's so intellectually challenging, but it is confusing. And in order for us to progress a bit faster, you need to digest this, and to digest this, I encourage you to read. That will be chapter 5 in Griffiths. And yeah. Okay, so see you on Wednesday, and thank you for arriving here.